we've had, up till now for chapter 5, we had obviously Rn is a vector space. What makes something a vector space is we would have, for example, V is a column vector. That's my objects, right? And then we have that V1 plus V2 and alpha V1 are defined, as normal, right? As the normal vector addition, scalar multiplication. And then we have the 10 axioms hold. So when we say things like you have a vector space, it means that you have your objects, the addition is defined, the scalar multiplication is defined, and these 10 axioms hold. Now, what we did on this is we took a vector space and we went ahead and defined an operator that was interesting. So if we defined that x inner product y, which is obviously x1, y1, plus everything up to xn, yn, as our scalar product, given that, we are able to talk about magnitude or length, and we would write that normally as a double bar of an object. It's just simply the scalar product with itself to the 1/2 power, square root. We could talk about the idea of angles, which was the cosine of theta was x inner product with y divided by the length of x divided by the length of y. And from that we have Cauchy-Schwarz inequality and being able to do projections and all this other sort of stuff that just came along with the fact that this was defined. So I'd like to do is go back and say, okay, we have these two things for Rn. The question could be, after all of this, is can we do the same idea for any vector space? So given a vector space, Rn, we had this new binary operator, right? Which is, binary means it's working on two things. And we called it the scalar product. But this took x and y and mixed it and spit something out. So it was a binary operator. We defined it. It was defined this way for the very specific reason is it allowed us to talk about lengths and it allowed us to talk about angles. So the question would be is, given any vector space, could you define a binary operator that would still allow you to talk about magnitude or lengths, which would really be just simply use the binary operator in a particular way, and it will spit out an idea of a magnitude or a length, and it would spit out the idea of an angle for that particular vector space. So we're going to still have our vector spaces, but we're going to add an entirely new operator that would then say, hey, this is going to involve angles, this is going to be involving in lengths. And we're going to eventually call these things inner product spaces. All right, what's an inner product space? An inner product space is a vector space. This is a vector space, which means what? It has objects, it has plus, it has scalar multiplication, all of the 10 axioms hold, so it's an actual vector space. And then we are going to add an operator. Now, here's the problem with symbology. What's the normal way that we do operators? I would like to have x and y to be somehow operated and spit out something, right? The way we did the inner product was we wrote it like this, right? What is the typical thing that, as you've done math, that a binary operator has normally been written?
Just something in between.
Just something in between. We do something like maybe an O plus, maybe something like that, right? That's a typical way that we do a binary operator. All right. The way we're going to define this binary operator is going to kind of look like a vector, We're not going to put something in the middle. We're not going to do an O plus. I mean, that'd be kind of actually, scalar product. We might have been to, I don't know, maybe make it look like a copyright notation, right? Or something like that. That's not what they do. What they do is they put angled bracket, first object, second object, angled bracket. So this is my symbology for the operator, which honestly, I think this is the only time I've ever, have you ever seen a binary operator that had 3 parts? The right side, the left side, and a comma in the middle. It's like usually been kind of awkward. Normally we just simply use parentheses if I have left and rights and with things in the middle. But this notation is just their choice of the notation. It's kind of classic. But what does this do? Well, what I do know is it's an operator that takes x, y, and returns a scalar. Right? It's a metric. It takes x and y and spits out a single number. Because that's what our scalar product did, right? It took 2 vectors and returned a number. All right. We get to add it. So what do you want? Anything you want. But it's going to have to do the things that the scalar product does. So it must satisfy that has 3 properties. The first property it has is that if I look back at what it does, the first thing it's working with is this idea of length, right? I took the scalar product with itself, and that was my idea of length. Does it make sense to ever have, if I say this is long, to ever return a negative number? Magnitude should always be positive. Especially if I look at this side right here, saying that this is the square root, right? That if I would take this and put it on the other side, saying that the square of the length should always be just simply the inner product with itself, because I'm taking the 1/2 power, because if I did something else, the 1/2 power would not make any sense. So the first thing that should happen is that if you take this operator, whatever you do, and you operate on an object with itself. So if I take a function with its own self, if it's continuous functional space. If I take a matrix with itself, whatever you do, it must return a non-negative number, either 0 or a positive. Now, when's the only time if I measure something, does it make sense to say that this table, if I was measuring in table space, and this is my table, and I said, hey, look, this table is of length 0. That's like kind of weird because I physically see it. What should be the only time in a vector space that you would get a length of nothing? What would be the only object in vector space that should return a nothing?
0.
The 0 object. And so not only should it return non-negatives, but also only the 0 object has 0 as its inner product. The second thing that happens should be that if I take the inner product between x and y, it should be equal to the inner product of y and x. This is it. Now, if I take an object with itself is how I get lengths, but an object with another object tells you about the angle in between the two. So if I say, hey, x and y have this angle, should that be the same thing as saying that y and x have this angle? And it's like, yeah, so it should be commutative. If I compare x to y and say how much they share, it should be the same thing as saying y and x, how much do they share? So it's going to be commutative. And the third property is if I would take alpha x plus beta y. So what am I doing? My vector that I'm looking at is actually a linear combination of 2 vectors. So if I say, hey, consider this vector, which has been found by taking a linear combination of other 2. So I have this resultant vector. And ask, what is the shared angle between it and a third vector? what should happen is it's the same as saying that it's a linear combination of the angles with x and z plus beta y and z. Angle contribution between x and z and a resultant vector is the same thing as the linear combination of z and x and z and y with the exact same scalar values. Now you can check that the normal scalar product did all three of these. And we define to say that any operator that does these three things is an operator that is useful for magnitudes and angles. Any such operator is called an inner product. So when we define within this class the word inner product, what it's done is it's gone up into whatever vector space you want, and it's saying, hey, define an operator however you choose as long as it meets these three properties. If it meets these three properties, this inner product is useful. Now, a vector space with an inner product put together is going to be called an inner product space. Again, note, any inner product xy on a vector space. So you have your vector space. We go ahead and define this operator however you choose to do it. Creates an inner product space. All right, so we've already done one. Example. Rn with the inner product defined as x transpose y. So what we do is we now have, okay, your space with this tool to measure magnitudes and angles. This satisfies because this satisfies the three properties. That implies that Rn with x transpose y is an inner product space. Again, what's nice about inner product spaces is what we've been doing. The inner product space is not only it's a vector space. I can get to places and have coordinates and everything else. It also has the ability to talk about angles and magnitudes. So all of a sudden we've been able to apply this idea of measurements within the space itself. So if you're imagining this room with all these arrows going however you want within three-dimensional space, by defining the scalar product, I can look at them and say, oh, I can talk about angles and I can talk about lengths. Where do I want to go? What angle do I have to turn to be able to get to that place? Those things are defined as long as we have this operator. But anything that satisfies those three properties will form an inner product space. So if I wanted to, I could just tweak this and make something that's a little bit different. Let's consider Rn. That's my vector space. And then what I do is I'm going to define my inner product by 1, consider W1, W2 up to Wn, all non-negative numbers. So I'm just going to pick some non-negative numbers. What? I don't care what. Just pick non-negative numbers. But now I'm going to define, and then 2, I'm going to say that xy, normally the normal scalar product is x1, y1 plus x2, y2 plus everything up to xn, yn, right? That's the normal scalar product. But now what I'm going to do is I'm going to weight. Hey, x1, y1, is only worth W1. But x2, y2 is worth W2. Up to xn, yn is worth Wn. So what do? Is I take a non-negative weight. Right? So that means that, not non-negative. I was thinking only positive, sorry. Positive weights. These are all greater than 0. So you just tell me how much x1, y1 is worth, and then how much x2, y2 is worth. And then just weight all of these accordingly, and that forms another inner product. Now, if I said it forms an inner product, what does that really mean?
It means it meets those 3 conditions.
It meets those 3 conditions. Well, we could actually check. Does this meet? What's the first condition? It must be greater than or equal to 0. Is that true? How do I do that? Because what is it? If I make it with itself, x1, y1 is really what? It's x1, x1, right? x2, y2 is really what? x2, y2. Really, what is this? This is equal to w1 times x1 squared plus w2 times x2 squared plus everything up to wn times xn squared. Now, is that a positive number?
Yes.
Yes, so I don't care what x is. x1 squared is going to be positive, right? Is x2 positive? Now, did I pick weights that were all positives? Yes. So what are all these numbers?
Positive.
These are all positives. So this has to be greater than or equal to 0. Now, since if I add up all positive numbers, if they're all greater than or equal to 0, so I'm adding up numbers that are all going to be greater than or equal to 0 individually, what's the only possibility to add a bunch of things and get 0?
They're all zeros.
They're all zeros. Now, is W1 ever 0? No. What does that mean x1 must be? 0. Is W2 ever 0? No. And so not only is this true, and this is only equal 0 if the xi's are 0, because the wi's are never. So first part is hold. Second, is x plus y the same, inner product xy the same as inner product yx? Well, let's look at this. What is that all? What is the only thing that's doing? Flipping those orders. Am I allowed to flip those orders? Yep. And so this is also true, because x1, y1 is the same thing as y1, x1. So they're equal. The third is much harder. This would be alpha x plus beta y z is supposed to be equal to alpha xz plus beta. It's not much harder. This is just algebra, right? You would sit there and go through this. For example, what would xz be? That would be x1 z1, x2 z2, xn zn, right? What would be yz? y1 z1, y2 z2, right? And we would have all of those guys at this big thing with all my weights, w1, w2, w3. An alpha that would put an alpha on everybody. A beta that would put beta on everybody. But if you would look at that and then do this left-hand side, you would notice that this is just the grouping property, right? You would just simply group and factor out. And if you would do that, the left and the right would still be the same thing. So this is also true. There's some algebra to do here. But it's just normal algebra. And this is also true. So guess what? A weighted scalar product is still an inner product. So I could have used that to measure space, but on the other hand, it's like, well, does this make kind of a natural application? And the normal scalar product naturally defined a true, where did this come out of? This came out of Euclidean geometry, right? But this would be angles and magnitudes for, essentially, Euclidean geometry is all the w's equal 1. Well, what if the w's take on other values? Kind of an interesting question. It wouldn't be Euclidean geometry anymore, but it would still be a space. It would have the angles and the magnitudes are different, but there's still a space. I can measure lengths and I can measure the idea of an angle. But because of this, I can take it out and do anything that I want. And so the typical inner products that we should know for each of the spaces. These are the two typical inner products for normal Rn. The normal scalar product and the weighted scalar product. You could actually do anything you want as long as it meets those three properties. But these are the typical ones that we use. Because these are the typical ones that we use, variants of them happen on all the spaces. So for example, matrix space with the inner product defined as, all right, what does the scalar product do? If I put two vectors beside each other, that x transpose, if I would have vector x, right, kind of go back up above. I'm going to erase this in a bit. So note, xy was doing what? It was taking x1, x2, say I only do x3, and y1, y2, and y3. What does a normal scalar product do? It just says x1, y1 plus x2, y2, those are supposed to be y's, plus x3, y3, right? What did it do? It said multiply same positions and then add. Could you take that and say, if it's multiply same positions and add, what if I took, instead of vectors like that, what if I would have, say, A, B, C, D versus E, F, G, H? If this is multiply same positions and add, it gives me a single number. Could I do something similar within matrices? Sure. How about we just simply multiply same positions and add? And hopefully, it will satisfy the three properties. And oddly, maybe not oddly enough. So how do I multiply same positions? Well, what are same positions? Aij, Bij. That's same positions, right? And now I add. The problem is the addition has how many dimensions?
N by n.
It's n by n, so there's 2 dimensions. So how many summations do I have to do? I have to sum the rows and sum the columns. And sum all of that together. How do I write a sum across rows and columns? It's a double sum. So this is a sum over the i's and the sum over the j's. I is in what? It's in row. So that means I goes from what? 1 to m. J is in the column, which goes from 1 to n. So for example, what would be the inner product of 1, 2, 3, 4, 5, 6 with -1, 0, 2, 1, 1, 1? What would I do? Just take same positions. What's 1 times -1? -1 plus, what's 2 times 0? 0. Plus, what's 3 times 2? And then 4 times 1. 5 times 1. 6 times 1. And so what's this inner product?
20.
It's 20. Just multiply same positions, add everybody up, you get a single scalar value. Well, so, right? So now that I have this like that, if that's my example, so that would actually say, so from above example, what is length? How did we calculate length? The length of a vector was equal to what? Square root. So that would tell me from above, my above example would become what? What is the length of any particular vector would be a inner product with itself, which is really what? So what would be the length of 1, 2, actually make this smaller number, so 1, 0, negative 1, 2, 1, 1, 1, 1. How long is that? Well, here's the nice part is, if you multiply it by itself, it's really doing what?
Squaring.
It's squaring everybody. Square every value. What do you have? 1, 0, 4, 1, 1, 1. Add that all up. What do I get?
8.
I get 8. So the answer is square root of 8, which is 2 square roots of 2. So within matrix space, with this inner product defined this way, how long is negative 1, 0, 2, 1, 1, 1? Its length, it's not really a length, it's the idea of a magnitude, is 2 square roots of 2. Interesting. Hey, how can I make that into a unit vector? Divided by its magnitude. Now it's a unit vector. So I can turn matrices, it's like a unit vector, even though it's a matrix, but the word vector is vector with quotes. Again, you would have to show, this is like one of the ones in the section, you just go through it and you show, hey, all three properties hold. Obviously, on the other hand, that would be that. What else could I immediately do with this? Instead of just having this normal inner product, I could turn it into a weighted. The classic way is to weight it. Just put W's on everybody. Just weight everybody, but when you weight, the weights all have to be strictly positive numbers, strictly greater than 0. So I could weight this and make a weighted inner product. The typical continuous functional AB would be to define an inner product, which would be a non-weighted inner product, so 1. What's the normal symbols that you use for functions? Instead of like x's and y's and v's and w's, what do we normally use? Like f and g. So f and g is the typical inner product used is to use the definite integral a to b of f of x dx, g of x dx. By the way, is this actually the same thing that we're doing up above? What does this symbol mean? Why is it an elongated S? Because it is a sum. What is this actually doing? This is taking the function f and the function g and then multiplying their heights, right? And then doing what? Adding the infinite number of them. So every one of these, I multiply that one and that number, get a number, and then adding them all from A to B. It's the same thing. It's exactly the scalar product, except it has an infinite number of things. I multiply them and add up those infinite number of things from A to B. And I get what? I get a scalar. But we could physically interpret this as what? It's the area underneath the product of the two-function curve. Again, does a little work, but you have to do some calculus. It satisfies all three properties. First off, it's pretty straightforward. What's the inner product of f of x and f of x? It's the square of the function. And if you square the height of a function, it's always positive, so the area must always be what? Positive. And what's the only time that this would ever be 0? If f of x is 0. That's the only area function that has 0 if it's above the curve. If it's at or above the curve, the only way for it to be 0 is if it's 0. And f of x, g of x is the same thing as g of x, f of x. What's the harder one? The alpha of f of x, beta g of x, right? All times z. But on the other hand, that's just a property of the definite integral. We could also take a weighted version. But now, how many weights do I need? If this is using an infinite number of heights between A and B, I need to have an infinite number. But what's the easiest way to represent that? A function. But it has to be what? A strictly positive function on AB. And then we would just simply say the inner product is now the integral from A to B of w of x, f of x, g of x, dx. And so this is just kind of it's a scaling. It's a stretching part that varies it. Typical weights that we use is a constant. right? Just pick a constant height and just simply stretch every one of these things by a particular value. But these are the two big ones. The normal inner product and the weighted inner product are still going to satisfy the three things, but we have to have a particular weight function chosen. Polynomial space is different. We still did the scalar, but we go back and say, all right, the scalar product required me to have actual values. Well, polynomial functions, if I said pick an infinite number of values from negative infinity to infinity, like I can't use my definite integral, right? Continuous functional space, I could use a definite integral because I was talking about continuous functions between A and B. Polynomial space is between what and what? Negative infinity to infinity. So this integral doesn't help me. I can't use an integral technique. But instead what we do is rather for polynomial space, is just randomly pick n spots. So you just go from, so polynomial space, if we do the normal inner product of it, we just, first thing is we're going to choose x1, x2, up to xn. Values. So I can go from negative infinity to infinity, but just pick n of them. Well, how many do I need? I need the exact same number as the number of terms for the polynomial. Why? Because this is necessary to have those three properties hold. So all we do is just randomly pick, if I have P5, so 5-term polynomial, pick 5 points. And then what we do is after you do that, you just simply say, two polynomials inner product would be equal to, take the first polynomial evaluated x1, which is a number, take the second polynomial evaluated at x1, add it to the first polynomial at x2, the second polynomial at x2. We keep adding it until we get to the last place that we've sampled, xn, q of xn. So this is exactly the true scalar product. But the numbers that we're picking are, go here, pick that height, that height. Go here, pick that height, that height. So I'm just sampling along this thing, and then I just do this typical scalar product. And then we do a weighted version, which is not only do we choose x1 to xn, we also have the weights w of x, which is still a positive thing, and then now my inner product pq is going to be, what is the weight at x1, what's the point p x1, what's the point q x1, and we just add them all up until we get the weight at the last sample, p at the last sample, q at the last sample. If you'd imagine what this would look like, if this is the p curve, and say that's the q curve, all we're saying is go here and pick those 2 points, and then go here and pick that point and that point, and then go here, pick this point and this point, until we get the, say, xn, where we pick, say, that point and that point. And then you can appropriately weight it by applying a weight function. So it's just really going through here and just creating a vector that's attached to the heights of p and attached to the heights of q to the normal scalar product. They're all based upon the scalar product. Why? Because the scalar product works. And since it works, I don't have to do any extra fancy stuff. It should come along and work as well. Picking n sample points is necessary to get a 0. That whole thing, that this thing has to be 0 only when it's 0. That's why we have to pick that many sample points. It ends up being solving a system of equations of homogeneous solution. The solution has to be strictly homogeneous, so we know it's only the 0 polynomial. That's where that one comes from. So any one of these, if you pick the vector space and then choose a corresponding inner product, you have an inner product space. What comes along? Well, given that you have any inner product space, we can, well, what can we do? One, hey, how big is something? Take the inner product and then raise it to the 1/2 power, just like we did with that polynomial. So we have lengths. So that means every inner product space, I could, hey, Rn with a weighted inner product, how long is this? Continuous functional space with this weighted inner product, what's the length? What's the magnitude? What it says is just simply take the inner product to the 1/2 power with itself. The second thing that we could do is we know angles. So since Cauchy-Schwarz is here, we have that if you take a x and a y inner product, right, which can return a positive or a negative value, and to take the absolute value, this is always less than or equal to what's the magnitude of x and what's the magnitude of y. This is the Cauchy-Schwarz inequality. But that means that these two magnitudes can be brought to the left-hand side. That's less than or equal to 1, which immediately says that a different variant is, hey, the cosine of the angle is just going to be the inner product divided by length of x, length of y. So that means that if I have, say, two matrices in inner product space for matrices, however choose to define it, I can actually say this matrix and this matrix have a cosine theta between them. So I'd actually take the arc cosine and say there's an angle between these two, which is really more along the lines of contribution. The bigger part of this is simply that x is orthogonal to y when their inner product is 0. That's from the Cauchy-Schwarz inequality. So I can declare them to be orthogonal. This matrix and this matrix are orthogonal. What that means is these two matrices within their space do not contribute towards one another. Changing values of one will not change any corresponding value of the other. So if we stretch one versus the other one, it's not going to cause the other one to have to change values at all. Think about that idea of contribution, right? If this one stretches, it's actually changing, this guy has a little bit to the right and upwards, right? So if I'm changing values of this, it's changing rightness because they have contribution. But if they were orthogonal, if this side stretches, what does it do to this guy here? Nothing. It doesn't contribute at all. So I can stretch that freely, and it doesn't do any contribution because they're orthogonal to each other. So the words orthogonal still make sense. It's about the idea of contribution. We have the Pythagorean law. If indeed their inner product is 0, which means what? They're orthogonal to each other. That would tell us that if you would want to find the length of x plus y squared, right? Just square the length so we don't have to worry about the half power. That's just equal to the length of x squared plus the length of y squared. That sure looks familiar. In Euclidean geometry, it's called the Pythagorean theorem. This is not Euclidean geometry. This is shapes and lengths within vector space, inner product spaces. So it's Pythagorean, but we call it the Pythagorean law. Not because it's Euclidean, but it's Euclidean-like. And it makes sense that if it worked in one inner product space and this form of an inner product works for other vector spaces, it still should hold. Along with that, we now get our projections, which is really just applications of these things. And so I could say, hey, if I would put x onto y, I could say that the vector projection is, what was the vector projection before? X transpose y, but what's representing that symbology? That's the xy inner product divided by y's transpose y, which would be yy inner product times y. Exact same formula. How long is that? This is called the vector projection. Its length would be called the scalar projection. And what is its length? It's going to be what? Xy inner product divided by the length of y. Where did that come from? That's from the cosine of theta is equal to what? Xy divided by magnitude of x, magnitude of y. And if I would have two vectors, right? If I would have vector, 90, vector, like this, right? And that's x, and that's theta. How long is the shadow? It's hypotenuse, which is length of x, times cosine theta, which is just simply going to leave that part right there. It's the same physical idea, though physically it doesn't look like that because this is not a Euclidean thing. Is everybody okay with that? That we've done this before? So it's exactly identical to the Rn space, except we have to ask what's our inner product and how does this work. So example. What if I said I had continuous functional space from -1 to 1, and I choose my inner product to be the non-weighted integral from -1 to 1 of f of x, g of x, dx. All right, I'm going to pick, say, three functions. Let's consider, say, function 1 of x is just simply 1. Let's consider function 2 of x is equal to, say, 1 plus x. Say function 3 of x is equal to, say, x plus x cubed. All right, we can do some different things. What is the magnitude concept of F1? Again, what's magnitude always? Its inner product with itself, all raised to the 1/2 power. What's the inner product if this is my inner product? So what do I need to figure out? What's the integral from -1 to 1 of? So that would be just simply 1 squared dx, and then I'm going to take it to the what? 1/2 power. Literally just use this as you see it. Right? What's 1 squared? What's the integral of 1? What's the integral from -1 to 1 of x? Right? So wait, let me get this wrong. No. I can't do it. Square root 2. I was doing the even odd too soon. Sorry. What's the magnitude of F3? Which is why I picked F3 for what it is. It's F3 to the 1/2 power, which is equal to the integral of -1 to 1. It's still going to be positive, right? So we were going to get x plus x cubed squared dx to the 1/2 power. This is uglier, which is what? I need to integrate from -1 to 1 of x squared plus 2x to the 4th plus x to the 6th. Still my 1/2 power. That's equal to Right, now, if we pause for a little bit, if I'm integrating from -1 to 1, and each of these are what? They're even, right? They're all of even power. A integration of an even, if these were all odds, what would be the answer? 0. If you integrate odd functions from -a to a, you get 0. If you integrate even functions from -a to a, it's twice from 0 to a. Right? So, anyways, this would be what? I could double everybody, and this would be 1/3 plus 2/5 plus 1/7. And I double it because of the evenness, right? And then I take this all to the 1/2 power, whatever that is. So those seem to be some odd lengths, right? But we can calculate them. How could I turn this into a unit function? So if I make it a unit function for f1, it would be just simply what? f1 over square root of 2, which is 1 over radical 2, is a unit function. So you can make unit vectors, it's a unit function. It's just its function divided by its own length. What about, can I find the angle from f1 equal 1 to f2 equaling 1 plus x? What's the cosine of theta? What would I do? f1, f2, inner product divided by length of f1, length of f2. So I've got 3 integrals to do. What's f1, f2? Integral from -1 to 1 of first function, second function, dx. That's the integral from -1 to 1 of 2 plus x, 1 plus x dx. That is what? Odd powered, so I don't have to worry about it. I just need to integrate the 1. So you're okay with that? So what is this? If we went, all right, if we do it the long way, x plus x squared evaluated from -1 to 1, which is equal to 1/2. Plug a 1 into this, we get. Plug a -1 into it, we get. But it's 1 minus a -1, so we get 2. But this, plug a 1 in, we get 1/2. Plug a -1 in, we get 1/2. They subtract to 0. That's why odds become evens from -1 to 1 drop out. And so I didn't have to worry about integrating that. I just get 2. But what was the length of f1? We already calculated it. Radical 2. What's the length of f2? Which is the integral from -1 to 1 of 1 plus 2x plus x squared. All right. That's odd. Don't need to worry about it, but if we want to do it, what's the integral of 1? Then that is? That one is? Which is 1 plus 1 plus 1/3 minus -1 plus 1, which is why I didn't need to do it. Those cancel. And then minus 1/3, which was why I just had to double those, right? So it's 2 plus 2/3, which is
8/3.
8/3.
Square root.
and then 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. So, what's the cosine of theta? So the inner product was what? 2. The length of F1? And then, which is 2 divided by 2, square root 2. Square root of 8 is 2 square roots 2 over radical 3, which that and that and that can cancel, and that's radical 3 over 2. So the cosine of theta is radical 3 over 2, and you can find theta however you want. And so that would be the contribution between those two functions. For which? This one? Or this is square root of 2 times square root of 2, since this is all over, that's over 1, right? And so that's 2 over 1. Square root of 2 times square root of 2 is 2. And those two with this 2 up above can cancel, right? Because that's denominator to numerator. And that's a denominator of a denominator, which is really a numerator.
So wouldn't it just be square root of 2?
No, because the bottom is 4.
You didn't cross
This,
out.
that 2.
Okay, I get you.
This one, and that one cancel, leaving that 2 right there. Because the bottom's actually 4. Okay. So everything that you were doing with Rn space, we can do with all of these. It just becomes a little bit more involved. And one of the things that we'll be interested in doing is showing things like, applications of such a thing would be if you could show, for example, say f1 is equal to sine of x and f2 is equal to cosine of x, show that that f1 is orthogonal to f2 on inner product space of a weighted norm from minus pi to pi of 1 over pi f of x, g of x, dx on continuous function minus pi to pi. And this is a classic example that you could do, which is, okay, I don't take just the normal norm, I take the weighted norm. So I take a uniform weight of everybody's 1 over pi, and then take f of x and g of x, I take my definite integral from minus pi to pi, and to show that, well, cosine and sine are orthogonal to each other. And then not only are they orthogonal, they're both of length 1. So then I can start to use these as the beginning bases for a span of objects, vectors, that are orthogonal and length 1 because they have nice properties. And so what really happens is you can go through this on this sort of inner product space is to take things like this, like 1, which we'll have to change, and say sine and cosine and sine 2x and cosine 2x and sine 3x and cosine 3x, etc. It ends up being that all of those are all orthogonal to one another within this inner product space, as long as we define this particular space as going from minus pi to pi. So we pick the continuous functional space of one oscillation of a trigonometric function, which is an interval of 2 pi. And then we can show that all these trig functions are orthogonal to each other, which would mean that these would be a good place to start as saying that, hey, use these as a basis set for a span, because they're all orthogonal. But it ends up being that you need to have an inner product and a vector space. And then you can start talking about orthogonality and length. All right, that's it.